Welcome back to Math for Technology. In this section we're going to do the second, in this video we're going to do the second section of chapter 14. We're only doing two sections, 14.1 and 14.6. In this section we are working on currents and AC currents circuits, specifically. Using Ohm's law, which is dealing with DC circuits, and make sure you watch the video that talks about the difference between a DC circuit and an AC circuit. There is a formula that is used by all electricians called Ohm's law, and it is V equals IR. So V is the voltage, that equals the current times the resistance. Now when you switch to an AC circuit, it's very similar, but it's V equals IZ. Since the circuit is now alternating, it's changing, it's not the same all the way through. We still have our voltage, we still have our current, but instead of resistance, we now have impedance. Now as we're working with this, we have what's called a reactance, and to find that we do XL equal, it's X equals XL minus XC. So X is our reactance. That is equal to our inductive reactance. Minus our capacitive reactance. Our impedance which is the letter Z as of above, our Z equals R plus JX, or because if we don't know X and we have to use our reactances individually, it would be R plus J times XL minus XC. And it could also be written as in a vector, where we have our magnitude and our angle, or our direction. If you don't know what your capacitive reactance is, you might have to find it. It would be 1 over angular velocity times your capacitor, or if they gave you frequency instead, it would be 1 over 2 times pi times frequency times capacitance. Or if you're looking for your inductive reactance, it would be your angular velocity times your induction. Or again, if you're given frequency instead, it would be 2 times pi times F times L. Now if we're working with it, we also need to find the magnitude and the phase angle. Our magnitude, just think back to vectors. So it's essentially the Pythagorean theorem. And if we're looking for our phase angle, it's the inverse tangent. If we're looking for our impedance in series, we do Z equals Z1 plus Z2. If we're trying to do it in parallel, then it's Z equals Z1 times Z2 over Z1 plus Z2. Okay, so we have all these formulas, and now we're going to go ahead and work with them. So if I want to find the total impedance in series, these are my given two circuits. So to find it in series first, remember it was just to do Z1 plus Z2. So 2 plus 3J plus 1 minus 5J. Put together my like terms. 2 plus 1 is 3. 3 minus 5 is minus 2J. And that's our answer. If we're looking for it in parallel, though, it's a little bit more work. The formula above was Z1 times Z2 over Z1 plus Z2. So 2 plus 3J times 1 minus 5J over, now we've already done Z1 plus Z2, that was our answer in A, so we can just go ahead and bring down our answer. We don't need to do it again. Now hopefully what you're noticing up above is that we have a binomial times a binomial, so we're just going to do each with each. So 2 times 1 gives me 2. 2 times negative 5J, it's negative 10J. 3J times 1 is 3J. 3J times negative 5 is negative 15J squared over my 3 minus 2J. Now, as we discussed in the previous section, J squared is equal to negative 1. So I'm going to substitute the J squared with negative 1, which brings my top to be 2. I'm going to go ahead and combine my J's. I end up with minus 7J. And I am subtracting a negative 1. I still have 3 minus 2J. If I subtract a negative, it becomes a positive. 2 plus 1 is 3. So I have 3 minus 7J over 3 minus 2J. Now it's not proper form, and it's the way that you see it now. We're not allowed to have imaginary numbers in the denominator. So we're going to have to multiply by what's called the conjugate. All the conjugate does is it changes this middle sign. Other than that, it stays identical, but I can't do it to the bottom unless I do it to the top. So I'm going to have to do each with each again, both to the top and the bottom. 3 times 3 gives me 9. 3 times 2J is 6J. 7J times 3 is minus 21J. Negative 7J times 2J minus 14J squared. I'm going to do it on the bottom. 3 times 3 is 9. 3 times 2J is 6J. Negative 2J times 3 is negative 6J. Negative 2J times 2J, it's minus 4J squared. Again, I'm going to replace those J squareds with negative 1. So my top is 9. I'm going to go 6J minus 21J. Gives me a minus 15J. I've got a minus 14 times a negative 1. And I just realized I totally screwed up above. So I did this, and that should have actually been a positive 15, which means that should have been 2 plus 15, or 17 minus 7J. Okay, let's work our way through this. So then 17 times 3 is 21. And then 17 times 2 is 34 instead of 6. 34 minus 21, I'm going to use the eraser on this piece since I found the root of it. So we're down to this, so it's 34 minus 21 forgot to get rid of the 9. So 17 times 3, did I write 21? Because 17 times 3 is 51. So I'm at 51. 34 minus 21 is 13. Okay, so I've got that piece fixed now. Minus 14 times negative 1. Okay, and nothing on the bottom got messed up. So I still have 9. Now the negative 6j and the positive 6j cancel, which is kind of the whole point of why we do the conjugate. So then if I look at this, all the negative 1 does is it changes this to a positive 14 and this one to a positive 4. So 51 plus 14 is 65. Still have the 13j. 9 plus 4 is 13. 65 is divisible by 13. So 65 divided by 13 is 5. 13 divided by 13 is 1. So I end up with 5 plus j. So sorry about that mistake, but we at least caught it. And I'll try and do a little bit better on the next one. Okay, oops, I'm going the wrong direction. So in this one, again, we're going to do it in we're going to find our total impedance in series and in parallel, but this time we're going to do it in a different form. This time it's looking like a vector. So it's 2.19 at 18.4 degrees, and it's 5.16 at 67.3 degrees. So instead of giving it to us as a complex number, it's given to us like a vector. In order to go ahead and do this through series, we're going to have to put them into their x and y parts. So we have to think back to when we did vectors. To find x, we did cosine, and to find y, we did sine. So our x1 is going to be 2.19 times cosine of 18.4. That is approximately 2.08. And then I'm going to do the second x. That's 5.16 times cosine of 67.3. And that is approximately 1.99. Remember, we add these together and I would get approximately 407. I'm going to go ahead and do it with the y's as well. So my y1 is 2.19 times sine of 18.4. And then my y2 of 67.3. Go ahead and add those. So now this is my x component, this is my y component. So to find the magnitude, I'm going to do the square root of 4.07 squared plus 5.45 squared. I'm going to get approximately 6.80. And then to go ahead and do the phase angle, we do the inverse tangent, 5.45 over 4.07, and we have approximately 53.2. So our answer would look like 6.80 at 53.2 degrees. I'm going to go ahead and make myself a little bit more room here so I can do it in parallel. So that was doing it in series. So that would be the adding together part, like the z1 plus z2. Now I have to do it in parallel, so if we think back, the nice thing about this when we go to do it in parallel is it's actually a little bit easier. So it was Z is Z1 times Z2 over Z1 plus Z2, and we just finished doing Z1 plus Z2. So our originals were 2.19 at 18.4 and 5.16 at 67.3. And then we already know our adding together gave me 6.80 at 53.2 degrees. Now the nice thing about this is we're going to go ahead and be able to do work with just the partials. So we're going to put all our magnitudes together. So we have 2.19 times 5.16 divided by 6.80. And then to do our angles, we're going to do 18.4 plus 67.3, and then we are subtracting 53.2. That ends up giving us an approximate answer when I multiply these together and divide by this of 1.66. Add these, subtract that, and I get 32.5. Okay, I'm going to go ahead and stop here, and that way if you need to stop and move on to something else you can. I'll come back and we just have a couple more to do and we'll finish up these notes.